Live stream is on, everything is on. Okay. Huh? Okay. Okay. So welcome to the last session. I hope you have still some energy left. I promise I'm not going to take much of your time. And hopefully I can give you some interesting perspective of the works that we are doing. Okay, so this is the last lecture of this track. The title of the lecture, as you can see, Intelligent Architecture for Intelligent Computing Systems. And let me just give you a brief background of who we are. So I'm Rahul, and that's my colleague Rakesh over here. So we are going to have the lecture. So we are the PhD students in Safari Research Group. Our main research interest lies in microarchitecture as well as storage and memory system design. That includes, let's say, prefetcher design as well as cache management, SSD management, and so on and so forth, all of these policies. We are also very much interested in data-driven architectures, and what exactly data-driven means, I'm just going to give you a perspective of in this lecture. And if you have any question, any follow-up thoughts that you want to share, you can reach us on this email address, both Rakesh and me. Okay, so with that, hopefully by this time, I'm not going to repeat all of these slides again and again, but I hope we have convinced you that today's computing is primarily bottlenecked by data, and data is the king. Be it high performance processing in server class workloads, or maybe let's say the workloads that getting executed in your phones, or maybe emerging workloads like what the lecturers prior to me have shown, like genomic applications. All of these workloads, they are tremendously generating data at much faster rate than what we can consume or what we can even process. So data essentially is becoming much more performance and energy bottleneck of today's systems. And so going forward, the axiom for us to design a high performance, energy efficient, power efficient processor is that, and any intelligent architecture, they need to handle data well. And data handling should be the primary and first and foremost, design choice of these processors. So what do I mean by, but then the thing is, in today's processor, it's completely on the other end of the spectrum. So what are the today's processor looks like? Then you have seen in the past lectures also, right, that they mostly devote most of the silicon space for only transferring the data rather than processing on the data, right? So we need a fundamental rethinking of the processing paradigm from a processor-centric approach to a data-centric approach, what Geraldo has mentioned, what Mohammed has mentioned, and also Nika touched in briefly. So I'm going to give you a background on the second part of this approach, that we also want these systems to be data, let's say, driven. So what do I mean by data driven? Like, for example, most of the design that we are doing in current processors, right? So these designs are like human design policies, which is kind of, let's say, stable at design point. Like once you ship out the processor, most of the fine tuning has done before, and after the processor has been shipped, not much tuning has been going on the fly. Like, for example, the phones that we are using in everyone's pocket, right? Let's say the memory controllers that we have in these phones, right? They are executing the same algorithm once that phone was designed, even though the phone has been seen your phone usage for quite a long time. So that's the problem that lies on, that even though we have like vast amount of data in front of us to learn dynamically on the fly, but still most of the algorithm that we are going to see in many of the throughout the hierarchy of the processor design, it's going to be statically fixed at design time. So that's what we need to change here. So we want some all of these policies coming from human design decisions to data-driven decisions. Let's say it would dynamically adapt on the fly on the field. And then the other part of this design policy is that it should be data aware also. Like data aware means, let's say, for example, depending on the type of the data. Let's say if you don't need the full precision floating point number, so if you don't need it, then your policy should also dynamically adapt itself, saying that okay, I don't need it, so my policy would change to auto precision. Let's say it would go to the lower precision scale. So that's the third design policy that we call it data aware. So for today's lecture, you have seen the data centric design a lot more detail in the past couple of lectures, right? And for this lecture, I'm going to focus on data driven architectures and what we mean by that. Yeah. Okay. Let's do this. Just give us a couple of time. What's happening?
This doesn't have an issue. It was fine before.
Autofocusing. Yeah. Okay. So where was I? Data driven architecture. So the data driven architecture is as I said, like the most of the policies that we see in throughout the processor design, right? So they are human designed, and human design the policy at the design time. For the designing, taking one design choice then the other, you had to make all sorts of decisions that also had happened at the design time, which cannot be changed at the runtime, right? So, and most of the cases, this design decisions that we are doing, they may tend up to be short-sighted rather than something that can take, let's say, long-term effects into account, right? So, and then definitely, as I said, like there is no automatic data driven policy learning that can adapt it, the policies that are inside inside the processor to be better with time, right? So, but then the question is that can we design some fundamentally intelligent architectures? So what do we mean by intelligent architecture? As I said, it's a data driven. That means it would automatically learn the best policy. We are not going to dictate what it should do. We are just going to tell it how it should learn, and it would learn and auto adapt the policies accordingly. And we are also going to give some examples. Let's say we can give these policies some sort of rewards that identifies that, okay, what sort of metric that it should chase to. And depending on that, it would try to optimize itself. It should be workload driven, and with the changing in the workloads, with the changing in the workload phases, it can auto adapt its decisions to make some far-sighted policy decisions. Okay, so but then the question is that all of this sounds nice. The question is, how should we start, right? I mean, okay, so just recall that this is what the typical memory hierarchy looks like, right? So you have different cores. Cores has some levels of caches inside, and then there is some last level cache which is shared across all the cores. Then you have memory controller backed up by the main memory, and then if some data is also not present in the main memory, then you have you fetch the data from the storage system, right? So that's. And beside these cores, you can also have in today's system, you can also have different types of cores. Like for example, GPU cores, you can have NPU cores and so on and so forth. All of these would probably talking to the memory controller, which would go to the main memory and which would further access the storage system if it needed. Now, so for today's lecture, we are going to focus on specific policies that we have designed throughout our research. So the first thing that we would touch upon is the RL-based prefetching mechanism. The second thing that we are going to show is an reinforcement learning-based DRAM controller policy. The third thing that we are going to touch upon is the RL-based hybrid storage system design. And if the time permits, the fourth thing that we are going to touch is a perceptron, which is not reinforcement learning, but some other type of machine learning driven off-chip prediction. What do I mean by off-chip prediction? Hopefully it would be clear by the time we'll go there. Okay. So with that, let's start with the first agenda, reinforcement learning driven hardware prefetching. So before going there, how many of you have, or let's say well versed with the reinforcement learning paradigm? Anyone? Okay, I see a couple of hands over there. Okay, that's good. And how many of you know what hardware prefetching is or prefetcher is? Okay, that's good. Okay, I don't see other hands. So maybe then I can give a very brief background of what prefetching is. Okay, so as the name suggests, prefetching means it's prefetch. So that means before the processor demands for a data, there would be some policy or some technique that's going to understand that this data is going to be needed in the future, and it would fetch the data wherever the data resides to the memory hierarchy. Let's say inside the cache, inside the processor, the last level cache, or the cache is closer to the core, whichever way we like, right? Why do we do this? Because memory latency is definitely high. So by the time the processor demands for the data and the data coming back from the main memory, the processor may actually wait for a longer time. So that's the main memory latency that's completely visible from the processor execution, right? But if we can predict that the processor is going to get this data in the future, and if we can proactively fetch the data even before the processor demands for it, hopefully we can save that latency. So by the time processor demands it, the data is already present in the cache, and you can simply access the data from the cache. Okay. So as I said, it involves predicting which addresses is going to be needed in the future. So this entire policy relies on how accurately or how much you can predict, and how much predictability is even there in the address access pattern, and that's the whole goal. Now, as I said, like the predictability can change, right? So if you can see, like all of these are the different memory access patterns which you can find in many of these workloads. Like if you see the first two access patterns, right? So they're very much regular. You can see the patterns apparently, right? One is the streaming access pattern. That the second one is they have some sort of delta in between, right? So that's very evident. But then as you go from the top to the bottom, right, so the pattern kind of becomes, much more harder and harder to identify. It's not that there isn't any pattern, but then there may be patterns, but then you need to look a lot, sophisticated way to understand what the pattern there is, right? So, but then the question is that if the policy is misidentifying some patterns, and then it's trying to fetch something that is not required, it's a misprediction, let's say. Does it affect correctness? Does it affect anything from the processor's perspective? The answer is no. It doesn't affect the processor's correctness. The execution still goes on. It's just that the policies dictates that okay, this data is going to be needed. It fetches the data from wherever the data was residing to the caches, but it's not needed. So it's just you did a wasted work. That's the goal. But then the thing is that the wasted work also has some side effects. Side effects in the sense, let's say, it wastes main memory bandwidth, it wastes the cache or the prefetch buffer, wherever you are putting that data inside, right? So it wastes that space. Obviously, it wastes the energy because you're doing some useless work. And, the list can go on. So the thing is that even if these mispredictions, they do not have any first order problems to the execution of the program, but they have second order problems, and the second order problems are also important depending on which type of system that you're looking at. So typically we have like prefetcher's performance kind of measured by these three horsemen of this evaluation: accuracy, coverage, and the timeliness. Accuracy being like accuracy and coverage, you can think of it as in the machine learning term precision and recall, right? Timeliness is basically how timely you are prefetching the data. Like if you have you prefetched exactly on time, or have you prefetched early enough so that by the time the demand comes from the processor core, your prefetch data is already arrived, or were you late? Let's say by the time the demand comes from the core, the prefetch data hasn't arrived yet. So these are the three main matrix that we evaluate the prefetcher with. But then there are also other other matrix like bandwidth consumptions and cache pollution and so on and so forth. As I mentioned, that they can also affect prefetcher's performance. Now the question is, you may be asking like, okay, on what sense they're affecting prefetcher performance? Do they have drastic effects on the overall performance? The answer is yes. So this is one work. Professor Pat is not here, so this is quite a bit of older work. But then the same takeaways that this figure shows, it's still valid in today's processor also. So what this figure shows that on the x-axis you have different workloads, y-axis you have instructions per cycle, higher is the better. Just think of it like this way. So on average, what we are seeing is that different color codes basically shows how aggressive the prefetcher is. So you can think of it from the left to the right, it's becoming more aggressive, right? So on average, if you see on average, every increase in the aggressiveness definitely improves performance. So you may conclude that life is good if we just simply keep on increasing the aggressiveness. But it may not be all for all the cases. Like if you see for these two workloads, actually it hurts performance. Now, why is the case? Because these workloads may be utilizing too much of memory bandwidth, so that if you employ the prefetching also, prefetching in the sense, prefetcher itself is also generating some request, which is colliding with the request that the core itself is generating. So it becoming garbled in the end. So in the end, the more aggressive you're making the prefetcher, the lesser the performance that you are going to get. Okay. Now, how to come out of this situation? So we can easily, see some sort of decision tree kind of matrix that, you can say that, I'm going to see what are the accuracy, right? So I'm going to bucketize the accuracy based on high accuracy, medium accuracy, and the low accuracy. And you can create some sort of tree saying that, if it is highly accurate, and then I'm going to check some lateness matrix. If it is not late, then I'm going to check some pollution metric. If it is not polluting, if it is polluting, then I'm going to decrease, I'm going to increase. So the whole point of this design policy is that you can come up with a simple technique like decision tree, right? You can say that, I'm going to look some telemetry data, try to understand if the telemetry data looks like this, I'm going to either increase the aggressiveness, decrease the aggressiveness. So if you do this, then as the paper shows, you can actually get average improvement on paper, but you can also get those two workloads that we showed in the beginning. Those two workloads also improve the performance. It's not actually reducing the performance. So just by having some sort of, let's say, adaptiveness gives you much more robust benefits than what you have seen in the past, right? Now the question is that, if you want to look into this paper more, definitely check out the link. But the question is that, can we do better? Decision tree is fine, but wouldn't it be nice if the algorithm automatically comes up with this thing? Why do you think that? Because we do literally have all sorts of telemetry data inside the processor itself. And we can simply try to understand that, if the telemetry data looks like this, performance actually degraded. If the telemetry data looked like something else, the performance improved. So you don't have to provide the algorithm to the design. You can just simply tell the algorithm what to check and how to come up with the algorithm, and then it would just dynamically figure with that. So with that, I'm going to discuss briefly about this work. It's called Pythia, a customizable hardware prefetching framework using online reinforcement learning. So what Pythia is essentially doing, it's kind of trying to, let's say, formulate prefetching as a reinforcement learning problem. So I'm just going to give a brief rundown of what reinforcement learning is. So reinforcement learning is kind of, let's say, an agent interacts with an environment, right? The agent kind of senses the environment, and then that's what we call a state information. For every state sensing, it takes an action. For every action, it gets a reward from the system, and then it uses the reward to try to correlate how the state impacts the action. So the whole goal is that we are not going to dictate how the state action correlation exists. We are just simply going to tell you how to understand this long-term reward, take into account, and come up with a policy so that at any given state, you're going to take an action that's going to give you a maximum reward. So that's the idea of reinforcement learning. Okay, so to do this thing, reinforcement learning uses something called a Q value for every state action pair. So what do you mean by Q value? You can think of Q value as an expected return. So higher the Q value, the higher the return that you can expect from that state. So, and given a state, typically the agent becomes greedy in the sense that, okay, if I'm in this state, I have, let's say, n possible actions. Which one should I choose? it would just simply look up its table, it looks up its database, whatever you call it. It would just simply look up and understand that the action that's going to give us the highest expected return, that means the highest Q value, I'm going to select that action. Okay, so that's the idea. So now how we are going to formulate prefetching as a reinforcement learning problem. In this case, prefetcher itself acts as an agent, right? And where the prefetcher resides, the processor and the memory subsystem, that acts as the environment where it senses. So for every demand request that the processor is generating, the prefetcher is trying to sense the state information. Like, for example, any feature that you can expect from this memory request. Like, for example, which program, which instruction generated this request, right? Or let's say which address this request is going to. What are the last, let's say, n deltas of address that you have seen? All of this information that you can think of, you can consider this as a state information. So now, given that state, you can take an action. So an action is as simple as, let's say, if the processor is demanding A, you are going to prefetch A plus O. So O is your action, okay? And you do that action, you get a reward for this action. The reward, I'm going to explain later what the reward is. And the reward is going to be used by the prefetcher to understand that, okay, given this state, whether this action was good or not, whether this action was bad, and you try to learn the correlation and go forward in the learning, okay? So that's the whole goal. As I said, like state information, that's what the state is. I'm not going to go too much detail into the state information. Action, as I said, that for every demand request A, your action would be just the prefetch offset. This is what we call a prefetch offset. So the processor is demanding for a cache line A, and the prefetcher said that, okay, from A, you go, let's say 10 offsets ahead, and A plus 10 is going to be your prefetch candidate. So 10 is your action, okay? And of course, 0 as an offset is also a valid action. So what do we mean by 0? It means that the prefetcher itself is actively saying that, okay, you know what, let's not prefetch anything. So that's a valid action in this case. And then we're going to show, like, we have techniques to make the prefetcher take this action also, depending on the situation. Okay, so then the most fundamental pillars of reinforcement learning is how exactly we are giving the reward. So reward in this case is encapsulating two metrics: the prefetch usefulness as well as some sort of system level feedback. Even though we have all sorts of system level feedback possible, we are going to demonstrate using, let's say, memory bandwidth as an example system level feedback. Okay, so this is what the reward looks like. You have accurate and timely, accurate and late. Loss of coverage means, the prefetcher said something that you cannot prefetch. So it's a legitimate possibility that you could have done something, but you didn't do. So that's a loss of coverage. And then you have some inaccurate and no prefetch rewards, which is further classified by, let's say, the bandwidth levels, right? So depending, you can think of it like this. I'm not, like, without going too much into detail, think of it in this way. So if your bandwidth is high, bandwidth usage is high, so you may actually trade off accuracy. You may actually trade off coverage for a better accuracy. Why? Because lots of requests are anyway going through that, the same bus that you are expecting. So maybe you should, not go for coverage. You should be very much accurate. But on the other hand, if your bandwidth usage is very low, so that means the entire memory bandwidth bus is probably sitting idle. It's not doing lots of transactions anyway. Then even if the prefetcher says that, you know what, I'm not sure about this prefetch candidate, but the algorithm would say that we have bandwidth, so why don't we let it go? So that's the idea. So we, just by setting these reward level values, you can actually change, and these reward level values can be changed on the runtime also. So you can change it on the runtimes and give a different objective to the same substrate, and it would behave differently. So that's the idea. Okay, so I'm not going too much into detail, but let's say this is one example of what reward looks like, right? So you have accurate and late, accurate and timely, which is, the plus numbers, which is a very high numbers than what we are providing for. Oh boy, okay, the slides are a bit messed up. Okay, so consider this -4, -2, -8, and -14, whatever it is. Okay, so the main key idea here is that if you're providing much more higher rewards for the accurate request, accurate prefetches rather than the no prefetch or the let's say inaccurate prefetch in the low bandwidth or the high bandwidth, it gives it gets a different sorts of objective. But then if you keep the same framework, but if you just simply change the reward levels. Now what I did that all of these rewards have stayed the same, but then the no prefetching low and the high reward, both the low bandwidth case and the high bandwidth case rewards became positive, and these inaccurate rewards become much more negative. So what does this means that you would either go for accurate prefetch whenever it's possible. If there is no accurate prefetch possibility, then it just simply it's beneficial for Prithia to just simply stay quiet, no prefetch anything at all, irrespective of the bandwidth consumption, rather than prefetching something rubbish. So this sort of design, if you just simply do fine tuning like this, you can actually get a much more conservative prefetcher right out on the box. Okay, and this sort of design can be improved for, let's say, server class processors as well as bandwidth sensitive workloads like that demands too much of bandwidth consumption. Okay, so with that, I would quickly go to the evaluation. I'm going to skip through the detailed overview, but if you're interested, definitely check out the paper. So with that, I'm just going to give you a very brief rundown of the evaluation, how it looks like. So on the x-axis, you have number of cores, right? So starting from 1 core all the way up to 12 cores. On the y-axis, you have the geomin speed up over the baseline. So higher the number, the better it is, right? So what we are seeing here is that, so these are, the prior works, right? So prior prefetches. So starting from 1 core all the way up to double core, and these systems, they don't have the same memory bandwidth, so that's why the trend may look different. But all you have to understand is that the performance difference from 1 core all the way up to 12 core, right? It actually changes for Pythia. So when Pythia has enough, when the system has enough bandwidth, Pythia improves performance than the prior best by, let's say, 3.4%. But let's say when you're going for a very conservative system, constrained system like 12 core per processor with much limited bandwidth per core, then you have, let's say, increased performance benefit out of that system. And the same trend remains if you look into, now this is a different way of visualizing similar kind of results. So let's say now we are seeing only 1 core, but we are changing the main memory bandwidth on the x-axis, right? So on the positive x-axis, you have the highest bandwidth. On the negative axis, you have the lowest bandwidth. And all of these bandwidth points are actually taken from real-life processors, right? So the per core available bandwidth of the real-life processors. And what you can see that, again, if you look into Pythia's chart, so that's kind of pushes the entire boundary across the board, right? If you have the highest amount of bandwidth available to the system, it still outperforms the prior best in class. But if you have the lowest amount of like really conservative systems, then the performance benefit improves by a lot. So the whole takeaway for you from this entire discussion is that the moment we inbuild the dynamic feedback into the policy itself, the learning-based mechanisms can provide better performance, better efficiency across the board, and that's what Pythia is showing over here. Okay, so do you have any other question before I go forward? Okay, maybe you can keep on saying. Rakesh,
okay, I just wonder what this prefetch happen, where this prefetch happens, in the L2 cache or the L3 cache?
Where the prefetch happens?
Yes.
Okay, that's a good question. So in this evaluation, we have made the prefetcher fills in the cache block up to L2. So the prefetcher sits physically beside L2 cache. So that means everything that comes out of L1 cache, L1 midstream, is visible to the prefetcher. It learns something, whatever we showed, and it can initiate a prefetch request. The prefetch request may come from LLC to L2. It may come from main memory, and it would get filled into LLC, and it would get filled into L2.
Yes. So the data here is based on the prefetch happens that L2 cache fetch the data from the L3 cache.
Yes, it's possible.
Okay.
Yes. Any other question? Okay, so if you're interested, definitely, the entire evaluation test bed is open source, and you can definitely check out this, other lectures also of this work, and that's the link of the paper itself. We have lots of other data, other evaluation points that I cannot cover right now, but if you're interested, definitely look into the extended version in the archive. Okay, so with that, I'm going to conclude the prefetching use case. Now let's go into move into a different use case. Again, we are going to use how reinforcement learning can be used in the other use case, but now we are going into a DRAM controller use case. Okay, so what DRAM controller is? So DRAM controller is basically the unit that decides how the commands would get scheduled to the DRAMs, right? So these are the requirements or the essential functions of DRAM controller. So what do they need to do? They need to ensure the correct operation is going on, like all the timing parameters, all the operations are scheduled in such a way that all the timing parameters are obeyed, right? And then it also need to, so that's the timing constraints, and it also needs to understand that, okay, is there any resource conflict, like boss level conflict, channel level conflict? It also needs to understand all of this information, and of course, so once it gets a memory request from the processor, it translates that memory request to a request that DRAM understands, right? So I'm going to show you one example of what the request looks like, and then it's also the prime point of ensuring fairness and quality of service. So fairness and quality of service means, let's say your DRAM controller right now in the today's processor, they can be shared across different types of cores, like CPU cores, GPU cores, NPU cores, and so on and so forth. So all of these cores, they have different sorts of applications going on. The applications have different deadlines to meet. They have different requirements to meet. Like, for example, let's say GPU applications are sending too many requests to the same memory controller. The CPU application, which is running on some one core, is kind of lagging behind, right? So the memory controller should ensure that nothing should be also starving, right? So you need to ensure some level of fairness. You need to ensure some level of quality of service, so that any applications should not get starved beyond an acceptable level. Any application should not be fall behind. Okay, so all of these things makes the life of DRAM controllers design itself very hard. Okay, so this is what a DRAM controller looks like. As you can see, like inside the DRAM controller, you have different queues for the banks, and then you have an arbitrator. So in this arbitrator, you have different agents that can send the request into, and then they would finally be sent to the DRAM chip itself. Okay. So this is what DRAM, let's say, operation looks like. So let's say you want a row from row 0, column 0. So the row address comes here, and then it would ask for the row. It kind of let's say reads the row 0 to the row the row buffer, and then it says that, okay, column 0. So I'm going to read column 0, and I'm going to send it to the requesting core. Okay, and then you're going to have, let's say, column 1. So you would read column 1, and then you send it to the requesting core, and so on and so forth, right? So now let's say if you request row 1, so the DRAM controller needs to understand that, oh, row 0 has been opened before. So if I'm going to access row 1 next, I need to pre-charge this row 0. So basically I need to copy it back to the main cell, right? So that's the row buffer conflict. You need to save it back first, and then you need to open another row. So all of this is kind of transparent from the application side, which is running on the CPU, right? So all of this is maintained by the DRAM itself, DRAM controller itself. Okay. So, and then on top of this, just to make your life hard, all of this, access, they have their own timing constraint. That, oh, you cannot have between 2 column accesses, you need to have this many time left. If you make it shorter, I cannot give you any guarantee of what data you are going to get. Between pre-charging, you need to have this many time left, right? So all of this timing constraint also need to be maintained by the DRAM controller. And this is just one example of the timing constraint that you have. And if you go into detail, it's just it's a very detailed design. So the DRAM controller needs to enforce as well as obey all of these constraints. Otherwise, you may actually get garbled data, which is not needed by anyone, right? So with all this, we have some naive policies, or let's say basic policies like first come first serve, right? So first come first serve says that, okay, whoever comes first, I'm going to give them, right? So that's a age old policy which appears in the real life also. And then you can have a bit more let's say tweak on top of first come first serve. Let's say first row first come first serve. So even if you have some, let's say request from two different rows are back to back, they came in the first come first serve level, but then there is another request which is also in that queue, but that request is going to the open row that you have. So then you would say that, okay, first row, then that means whichever is the open row, you are going to serve that request first. And then if there is no request left for that row, you're going to close it, and then you're going to get it some next. Okay. Now, but the thing is that this is one way of probing into, making it more performant. But then there can be lots of other features that you can understand, like, oh, what is the age of the request? What is the whether the request is going to be row buffer hit or miss? That's what FRFCFS uses for scheduling its making its own schedule. But then you can also have, let's say, request type, requester type, request criticality. This is another like a very very key word, right? So which request is critical? Is this the oldest miss in the core? Is this core is going to be much more painful to the core in terms of, let's say, losing performance, right? So those things you can also take into account. Now all of this is just making your life harder. Like you need to satisfy all the constraints. You need to come up with all of these techniques. I mean, what's going on? Right. So the question is that, can we not make our life easier? Right. So that's the whole idea, that, okay, let's make the life easier. Let's offload the entire design complexity to the learning thing itself. Again, RL to the rescue. So what we are doing, we are saying that, okay, so it's definitely difficult to design. So the key idea is that the memory controller that adapts its scheduling policy to the workload behavior and the system conditions, it would use some sort of auto learning mechanisms, like machine learning mechanisms, to come up with this policy by itself, right? So that's a whole idea of the this work, that we are going to use model memory controller as a reinforcement learning agent. So what do we mean by reinforcement learning? Again, the same thing. I'm not going to go and repeat this again, but the agent is the scheduler itself, right? And it's going to like the state action, the state information that the scheduler is taking is all the state attributes. You can think of every type of the list that I showed, the laundry list, right? So you can think of everything as a state attribute. So whether the request is a read or miss, is it going to be a row buffer hit or miss? What is the age of the request? What is the who is the requester core? Is it critical? All of this information can be used as a state information, right? Using that information, you are going to take an action. The action is as simple as, I'm going to schedule this command. That's it, right? And you're going to get some sort of feedback into the system. The feedback is as simple as, let's say, has I scheduled any read request or a write request, which is basically progressing the machine. If that's the case, then I'm going to give you 1 reward. If you haven't done it, I'm going to give you a 0 reward. And that's the whole goal. And if you just keep and then you have all sorts of the learning principles, the SARS algorithm. If you are interested, definitely check out the paper. And if you just simply define these 3 pillars of reinforcement learning and let the agent go, it would just simply automatically come up with the policy that gives you the best DRAM bus utilization. And that's the whole goal of this policy, right? So as you can see here, that, okay, you have a different you have a transaction queue. All the transactions coming from the core is getting submitted to this queue, and then every entry in the transaction queue has all sorts of information, and you can use this information as a state information to get some action. That action schedules a command to the DRAM. You would get a reward, and that's how you close the feedback loop. Okay, so that's the list of actions that you can take. Let's say activate, write. Oh, I have a question. Yeah.
Okay, how big is the meta information, the training meta? How big is this?
Okay.
Overhead with all of this RLE?
That's a good question. So the overhead can actually vary. In this case, we need to optimize the system for, let's say, faster operation rather than the coming up with the best possible scheduling policy. So that's why what we use in this case is a very simple tabular method. So the tabular method works in a very low overhead, let's say, in the orders of KBs. So for every state information, you are going to quantize that state information into some bits of buckets, right? And then for every bucket of that state information, you are going to have all the actions, which action had how much of Q value, and you are just going to increment that. So using some sort of, let's say, quantization as well as generalization, you can trim down the area overhead of these policy into orders of KBs.
Okay, follow-up question.
Sure.
You said that this is beside the L2 cache?
No. This one is a DRAM controller. The previous one sits beside L2 cache. Yes.
So that is also all the paths from L1 to L2. This path from L1 to L2.
The prefetcher.
Yes.
No. So the prefetchers. Okay. So think of prefetcher acting like this. So every time when you have some request coming out from L1, the prefetcher observes it. It's not on the prefetcher's action is not on the critical path. The demand request goes on the critical path because the processor is waiting for that data to come back, right? Prefetcher is, you can think of it as a sideline. It's just simply observing, okay, it's going on, it's going on. I'm just learning something, and I'm also pushing something onto the memory hierarchy. Me as a prefetcher, my whole goal would be to fetch something before the processor demands into the L2 cache or the LLC itself. So prefetcher's request itself is not on the critical path. Does it make sense? Okay, that's a good question. But the thing is that all of these critical, whether a policy or whether a component is on the critical path or not, it actually dictates how much latency we can afford for that. And I'm going to touch up on this next after Rakesh's presentation. The last policy, the last example that I'm going to give you, it actually sits exactly on the critical path. So there, we need to be much more careful and much more innovative. That's a good one. Anything else? Okay. So if not, then I'm just going to just wrap it up on this one. So as I said, like if you go on as a reinforcement learning based policy, like on this graph, you can literally see this is the in order one. That means what in the whichever way it's coming on, you're just simply processing it in that way. Then you have the FRFCFS policy, you have the reinforcement learning based policy, and then you have the optimistic policy, which has the future information, like the literal optimistic way of scheduling, right? So you can consider this number as the headroom that you have, and we are all chasing on that headroom. So as you can see that even we normalize this thing with the FRFCFS policy. So as you can see, like if you go for just in order based policy, it's actually detrimental to performance. But a reinforcement learning based policy, it starts from scratch. It has no idea to begin with, and it just catches up. It not just catches up, it actually improves performance. So that's the beauty of it. And even the better thing is that the different type of workloads that you are going to throw at, different type of configuration that you're going to throw at. Let's say, for example, in this case, right? So you have one channel, and then you have also two channel systems, right? The same trend shows that from one channel, all of this is normalized to FRFCFS one channel, right? So in one channel, you are anyway seeing 19% performance improvement. If you have two channels, then the baseline also improves the performance. But then RL, if you provide RL on top of that, it improves performance even more. So the whole takeaway that I want to give you in the end is that it's possible to have dynamic policies that simply starts from scratch. You just simply tell it how it should learn. You don't dictate what it should learn, and it would automatically come to a position where it would start making correct decisions and improve performance. So this is not only useful for, let's say, supporting a wide range of workloads, but wide range of system configurations. Anything that you can throw at it would just simply dynamically adapt. Okay, so if you are interested, definitely check out this paper. But then before going forward, I just wanted to briefly touch upon this point just as a food for thought. You may actually say that, okay, the reward is the fundamental pillar. Like if you tune the reward, it can go actually haywire. It's just like human as a like bringing up from the baby to the adulthood, right? So if you're giving a different reward, it would just simply become a different person. As simple as that. So now the question is that you have seen a reward structure that only uses DRAM bus utilization, right? You may actually ask that, okay, can we not give different rewards also? Let's say that is more encompassing than just the DRAM bus utilization, because DRAM bus utilization is in a sense, it's acting as a proxy of performance. But performance is not the only concern here. How about the fairness? How about the quality of service? So if you want to add that, you can actually change the reward structure in your way, and you would see that the algorithm would again automatically adapt in its way. So if you want to read that, so this is one the work that I just discussed now. But then there is a follow-up work also, as the name suggests. It's a multi-objective reinforcement learning-based memory DRAM scheduling policy. It's built on top of what the prior work said, and it not only just goes in a one-pronged system, but it's a multi-pronged optimization. And you can literally use the similar type of technique on different types of systems also. Okay. So with that, I'm going to pass it over to Rakesh, and Rakesh is going to discuss more about the storage system and usage of reinforcement learning in the storage system. You can use this.
Thanks, Rahul. So I'll be presenting a work which again uses reinforcement learning, but it uses it in a different context, in a category of systems called hybrid storage systems, which do not have the constraints, especially the latency constraints that are imposed on the cache subsystem or the main memory subsystem. So this work was published in ISCA 2022, and it's called Sybil, an adaptive and extensible data placement in hybrid storage systems using online RL. So I'll start with a bit of background on what hybrid storage systems are. And here you just combine multiple storage devices with diverse characteristics. Here you can see an Intel Optane SSD, which is a very high-end SSD with low latency access and rotating hard disk drive. And you also have a storage management layer, which is basically the brains of this system, which kind of exposes a unified address space of which combines both the capacities of these devices and presents a unified address space to the applications. And applications can read or write to these devices, and then the storage management layer decides where to put the data. And so another responsibility of the storage management layer is to also migrate the devices or move the data between the two devices. This is a very rudimentary representation of hybrid storage systems, but in a real environment, you may have tens of devices. And so the performance of such a system highly depends on the storage management layer's ability to perform these the data placement and data migration in a very effective manner, and also manage different devices and the workloads. So what we did was we looked at the current policies that are used for data placement and data migration. Here I talk about data placement only, and we identified two key shortcomings that significantly limit the performance benefits of these techniques. One is lack of adaptivity. So I'll show some data on this. And then there is lack of extensibility. So these policies cannot be used as is when the number of devices change in the hybrid storage system. So one reason for lack of adaptivity is if the workload changes, then these prior data placement techniques they consider only a few characteristics like access frequency or access recency, and they're all statically tuned. So here I would like to point you to two things. One is CDE and an Oracle approach. So CDE is basically a heuristic policy that only looks at access frequency, and you have an Oracle approach that has knowledge of future access patterns and makes decisions based on that. So here you can see that compared to an Oracle policy, CDE performs slightly better in a workload called HM1, and you see that there is a large difference between Oracle and CDE in PRN1. So these policies don't really perform well as if the workload changes. Similarly, when you have the underlying environment, if it changes, then these policies again do not perform very well. So here you can see that I don't know if So we show the average request latency, and I would like to point you to slow only and CDE again. So here you can see in one of the configurations the CDE performs worse than the slow only policy, which is where you write the data, all the data to the slow device. And then if you change the configuration and run the same policy, you see that CDE performs much better in that configuration. So then there is the lack of extensibility problem, which is these techniques are hand designed, or they rely on thresholds. And if you have a 2-device configuration, it can work. But if you have a third device, then you have to change it and change the policy and add more thresholds. So this is these are the limitations of prior approaches. So what we set out to do was to design a data placement mechanism that can provide both adaptivity and extensibility. So to this end, we propose Sybil, which formulates data placement as a reinforcement learning problem. And I'll give some background, but I will not necessarily go to the details of RL itself because you have already seen that. So how do we formulate data placement as an RL problem? So you have an agent, and in our case, we have Sybil, and the environment is the hybrid storage system. And the agent reads the state from the environment. So here we provide features of the current request, the incoming request from the application, and then also look at the system for metadata. And then Sybil can perform an action, which is to decide where to place the data, whether to do it in the fast device or in the slow device. And the agent and the system gives a reward. And in our case, it's based on the request latency of the last served request. So let's again quickly look at what is the state. And here you can see a 6-dimensional representation of the state features. It contains a lot of information from the application request, like the size, the type of the request, the access interval, access count, and also looks at this environment details like capacity of the fast device and also where the page is currently placed. And we selected these state features based on rigorous feature selection. And we also wanted to reduce the metadata, so we stuck to a very limited set of features. And to further reduce the metadata overhead, what we do is we quantize the state representation into bins, which means that the size can be represented only by a few size classes. So if we move to reward, which is the most important aspect of a reinforcement learning agent, as Rahul mentioned, here it also defines the objective of the RL agent. And here we formulate the reward as a function of the request latency. So what we do is we always provide the request latency of the previously served request as the reward. And if the request latency is lower, the reward is always higher. And in our case, what it encapsulates is it also captures the internal state of the device. And if there are evictions caused because of the fast device being full, then that also gets captured. So by no means this is the best reward that we can construct. And in the paper, we also show that we explored more reward functions. And I would like to point you to the paper on this. So then the action is pretty simple. So if you have two devices in the system, then it decides to place the page or the request into the fast storage device or the slow storage device. And if there are multiple devices, then it can decide on which target device to store the data. There are a couple of limitations with Sybil that I need to mention. So if Sybil kind of puts a lot of data into the fast device and the fast device capacity reaches 100%, then it evicts the data to place new data. And it also promotes a page, which means that it moves the data from a slow device to the fast device only when there is an update from the application. So I'll quickly go over the design of RL of Sybil. And Sybil has two threads. So there is a RL decision thread which takes the storage request and also looks at the environment, and then it makes a decision on where to place the data. There is also a RL training thread which learns all the information, the state of the system, the reward, and the action, and then it basically trains the neural network. So unlike Pythia, here we use a simple feed-forward neural network, and which has two layers, and this training thread basically trains that network, and it periodically updates the policy weights so that the decision thread can make good decisions or adapt to changes in the workload. So this is an asynchronous mode of execution. So what this design does is it actually reduces the burden on the RL decision thread, because that is in the critical path of the IO request. So this basically removes the training from the critical path and places it in the background. So this is a kind of a magnified image of this previous slide. So we get the storage request from the application, and we also look at the environment for the features, and we form an observation vector, and that basically is fed as a state to the inference network, which is again a simple feed-forward network. And the objective of this network is to maximize the reward, and basically that, I'm sorry. So it provides an action to the hybrid storage system, and the state changes when the action is performed, and then the system gives a reward to the RL agent. And all of these, the state, action, and reward is captured as an experience and is stored in the experience buffer. So this is the responsibility of the RL decision thread. And so the training thread picks up these experiences in batches, and this is used as the data set for the training network. And so once the network is trained, it periodically updates the policy with the inference network, and it helps in adapting to workload changes and the system conditions. So that's basically, in a nutshell, what Sybil looks like. If you have any questions, I'll be happy to take before I go to evaluation. So the Sybil, the hardware is basically, you can say that if you have multiple devices, that is connected to the PCIe interface, that is hardware. But where this agent is running is in the storage management layer that I showed in the background. So that is, if I need to explain further, then it's basically like a kernel implementation that we have that's in the operating system. It's like a block driver that you can imagine.
So if I'm right, this is on the DRAM.
Which one? No, this is a completely different domain. So what you're looking at is a storage system. Yeah. So the controller is basically running in the operating system. It's not a hardware controller, but it's basically done in the software. Okay. Any other questions? Okay, I'll quickly move on to the evaluation. So what we did was we tried to evaluate Sybil and prior approaches on a real system with different configurations. We have a dual hybrid configuration and a tri-hybrid configuration. And we basically perform the training and inference on the CPU. So here you can see two configurations, a cost-oriented configuration, which is a high-end SSD and a hard disk drive, and a performance-oriented configuration with a high-end SSD and a middle-end SSD. So we evaluate on 18 different workloads, and we have 4 prior approaches, which are 2 of them are heuristic-based and 2 of them are supervised learning-based approaches. So I'll first go with the results of cost-oriented HSS configuration, and here we only look at the average request latency, and hopefully Sybil has lower request latency than all the prior approaches. So Sybil consistently performs better than all the baselines in cost-oriented configuration. And on a performance-oriented configuration, you see that Sybil provides 21.6% improvement over the prior approaches. And it also achieves 80% of the performance of an Oracle policy that has complete knowledge of future access patterns. So that's what you are seeing here. Yeah. So then we look at how we can extend Sybil to 3 devices. And we show that it's pretty easy to extend Sybil because we just have to add another action into the to the RL agent, which means you just have to add another neuron to the output layer of the neural network. And you also add the remaining capacity of the new device as the state feature. So here we actually found it difficult to find a good baseline to compare with, but we had to develop a good a baseline ourselves. So we extended the CDE approach, and so Sybil, as you can see here, Sybil has a lower average request latency compared to the heuristic approach, and it actually outperforms the policy by 48.2%, and it also reduces the system architect's burden by providing ease of extensibility. Now, coming to overhead, which is important, the total storage overhead for the experience buffer, the inference network, and the training network is around 125 kilobytes. And then we also have to store a lot of data to train these networks, and the metadata overhead for each page is around 40 bit. This is a limitation that we have to address, because if you have a large number of pages, then you have this metadata can increase. But because of the asynchronous execution, the training latency is around 2 microseconds, and the inference latency is in the order of nanoseconds. So it doesn't add a lot of latency overhead to the critical path of the IO request. We have a lot more results in the paper, and especially things like unseen workloads. So we configure the hyperparameters on a set of workloads, and then we run the evaluation on a different set of workloads. And then we have mixed workloads where we run parallel applications. And then we also show the evaluation for different hyperparameter values and so on. And the main thing is that we also try to explain the actions of Sybil and for different workload characteristics and configurations. So this is the link to the paper, and we also have open sourced the code of Sybil, and you can find it in this GitHub link. So in conclusion, Sybil is the first reinforcement learning-based data placement technique in hybrid storage systems. And it provides adaptivity, extensibility, ease of design, and implementation. We evaluate Sybil on real systems, and it provides significant performance improvement over the prior approaches. And also it can be extensible, and it provides good performance improvement. So I'll briefly touch upon some major directions that this work can enable, and also kind of give you some food for thought. So as I mentioned, that the reward structure gives an indication of what is the objective of that we are trying to optimize. And what we tried to optimize was latency, which means we are only looking at performance. But there are other aspects that we need to consider in a storage system. For example, energy efficiency. We also need to look at endurance of the storage devices, which means that we need to have a more comprehensive reward structure, like Rahul mentioned. And that's an area of research that we would like to continue. then you also saw that Sybil is only looking at data placement. But there is also the policy of data migration, which means that if you keep placing the data in the fast device, then at some point it gets fully utilized. So you need to move some data. So then the question arises, which data to move, when to move, and what to move. So these are some questions that can be answered with effective techniques that depend on machine learning. And if you have more such machine learning techniques, then how do we coordinate these multiple techniques and try to improve the system? And lastly, how do we take these approaches or take the learnings from these approaches and implement it in other systems, which are heterogeneous again? So you have a DRAM plus NVM kind of a system, and you also can create a heterogeneous system with CPU caches and DRAM. So the challenge here is to consider the latency requirements of these systems. And as you keep going into these territories, you see that the latency constraint is very critical, and you need to design these policies based on that. I have to mention that because we are in the storage domain in the hierarchy, we have some leeway to kind of explore, have more complex neural networks to use, and that gives us good improvement. But as we move to other subsystems, we have to look at the latency. So with that, I'll close my presentation and I'll hand it over to Rahul. If you have any questions, please let me know.
Any questions?
Okay. Then thank you so much.
Okay, so I prefetched. Okay, so we are going to briefly touch upon the last one on this series, and then one of my colleagues here, Konstantinos, he's going to, give a final thoughts on the research directions that he's also going on. Okay, so since Rakesh has already mentioned, machine learning, all of these things, fine, looks good. Maybe we need to also keep an eye on the latency that these policies actually use. So I'm going to use, I'm going to give one demonstration of one policy that is definitely on the critical path, as you mentioned, right? But it also tries to hide the latency from the memory access. So let's see how it goes. So this is called Hermes, accelerating long latency load request via perceptron-based off-chip load prediction. So the key thesis of this work revolves around the long latency off-chip loads, like basically load requests that the processor is demanding. That data is not present in the on-chip cache hierarchy. It needs to come from the off-chip main memory. Okay, so now these sort of requests, they are the main culprits of processor performance. Like they are the ones who the processor waits on that data to come back. By the time the data comes back, the processor has exhausted all the level of parallelism that it can exploit. The ROV gets full, blah, blah, blah. It basically limits the performance, right? So if we can reduce the latency of these off-chip load requests, that's the whole deal of improving performance. And prefetching is one technique that we have shown to be effective. I'm going to show you another technique on this direction. So to reduce the latency of such off-chip load requests, the prior walks or the traditional techniques that we typically employ is sophisticated prefetches, as we have seen before. Pythia is one example. And then we also have this tendency of increasing the on-chip caches, because the bigger the cache, more data that you can cache inside. So hopefully less and less amount of data that you need to fetch it from the off-chip main memory. Okay. Now, what we have seen in this work is that even though you have, let's say, state-of-the-art, most complex, high performance prefetcher deployed, still the pie chart looks like this. So 50% of the requests that would have gone off chip kind of gets saved by the prefetcher. It already gets predicted, gets back to the cache before the processor demands. But then the other 50% still goes on. Like you save the problem by half, but then the half still remains. That's a whole takeaway. Now, from this half of 50%, if you look into them, like how many of these requests are still blocking the instruction retirement from the reorder buffer, 70% of these off-chip load requests are still blocking the instruction retirement. So they are still critical to performance. Okay. Now, if we look into that 50% of that memory requests that are still going off chip, and if we try to understand where the latency is getting spent, now what we observe is that on-chip cache access latency are not small at all. So this is the typical timeline that you normally see, like L1 access, then followed by L2, followed by LLC, and then the main memory access. But then on-chip cache access latency by itself also takes a lot of time, right? Now, what we again, the animation is screwed up. Okay, so what we observed is that, wow, it's not even there. So what we observed is that if you can predict that, oh, this request is going to go to main memory. So what you do with that prediction? You would say that, okay, right when the prefetcher is right when the cache hierarchy is getting looked up, you would also start an access to from the DRAM. And you would say that, okay, fetch the data. So if the prediction goes right, then the request would eventually arrive at the DRAM, the main memory controller. And by the time main memory controller would hopefully say that, you know what, that request is already pending. I have issued the request from the DRAM, it's coming on. Why don't you simply wait? And once the data comes back, I will just simply give it to you. So basically what you can do is you can parallelize this, the timeline. It doesn't need to look like it's happening everything in serial. While the L1, L2, LLC cache lookup is happening, you can also start making the main memory accesses. So that's the whole goal. The animation is not here, but think of it like this. Okay. So now the trend that we are seeing is that this is a pretty, older work from 2007. What it shows that, the caches are growing bigger and bigger. So the latency is not getting smaller anywhere. And we see the similar pattern, in recent times also. As a matter of fact, like by the time we actually started this research, back in 2021, Golden Cove is the latest generation architecture from Intel. It used to have, let's say, 1.5 on 1.25 MB of L2 cache at that time, which is taking almost around 15 cycle of CPU latency. By the time we are presenting this paper, newer architecture came in. It became 2 MB cache, and then again it clocked back one cycle more. Now, day before yesterday, or I think a couple of days back, Intel released another architecture, which is called Lunar Lake. I think they increased the this size from 2 MB to 2.5 and up to 3 MB now. And now instead of having 16 cycles, now it's even taking 17 cycles. So the trend, it shows that the caches are not going smaller because you need to cater bigger data footprint, right? And the bigger the cache size become, the longer the latency the cache itself takes to access. Like the technique that tries to save latency eats up latency in the end. So yeah, I mean, it's a dichotomy. So the whole the goal of this paper is that, as I showed earlier, that we want to improve the processor performance by removing this on-chip cache access latency, which is now happening on the critical path. We would try to take it from the critical path, and it would put it from the critical path of the off-chip load. So off-chip loads can start accessing the off-chip main memory as fast as possible. It doesn't have to go through the entire cache hierarchy lookup and then say that, oh, you know what, the data is not there. Okay, so that's the whole goal, and towards this we propose Hermes. Hermes based on its two key ideas. The first idea is that it predicts, as I said, it predicts which load request is going to likely go to off-chip, and for those predicted requests, it would simply start fetching the data directly from the DRAM while the data access is still going on the cache hierarchy. So the idea is that by the time the data comes back from the DRAM, same time maybe later the cache hierarchy lookup would also finish, and it would arrive at the memory controller, and memory controller would say that, okay, the request is already going on, and once it receives the data back from the DRAM, it would just simply return it back to the code. Okay, so towards the key contribution of this paper is that it proposes the first perceptron-based off-chip load predictor. I'm just going to give you a brief background of how the perceptron prediction looks like. And this perceptron predictor predicts which load requests are likely going off-chip, just simply learning from program information rather than tracking any other metadata. Like, for example, oh, I'm going to track all the tag of every cache lines that are present. It doesn't go on that direction. It just simply tries to learn from the program access pattern itself that, okay, if this feature repeats again, it's likely that this request is going to be off chip. Okay. Okay. So I'm not sure whether the animation would stay live. Oh, it's live. Okay. So this is what the cache hierarchy looks like, right? So L1D, L2, LLC, then memory controller, and then the off-chip main memory. So what you can see is that, okay, if you are accessing in the baseline access looks like this. If this is the latency tolerance limit of the processor, like that means your processor has some sort of, leeway to, while it's waiting on the data to come back, it can also exploit the out of order execution to make other executions going on at the same time. But eventually that would also finish because the processor would then start stalling completely. So if this is the tolerance limit of the processor, the remaining time, it would just simply start stalling. So what Hermes does is Hermes employs a perceptron-based off-chip predictor, which we name Puppet. So for every request that is generated by core, Hermes first asks Puppet that, oh, is it likely going to be off-chip? If Puppet says that it's going to be off-chip, it would simply start access. It would wait. Oh, wait. So it would wait for the address translation to finish, because note this, main memory is always going to be accessed using physical address. But then the address that the core is generating is actually on the virtual address, and it comes with lots of problems. Konstantinos has briefly touched upon it before. Konstantinos is going to touch upon it again. That the things that we take it for granted may not be actually for granted also. But anyways, so typically what happens is that the translation happens in parallel with the L1 data cache lookup. So it would just simply wait for the L1 data cache lookup to complete. So by that time, you would know the physical address. Then what Puppet does, it would directly issue a request to the main memory controller. And the main memory controller would say that, oh, I'm going to get the data from the off-chip main memory, while the request is still flowing through the cache hierarchy. If the prediction is correct, it would eventually arrive. In this case, it didn't arrive. Okay. If the prediction is correct, it would eventually arrive at the memory controller. At that time, if the data is already came back from the DRAM, it would just simply wait. It would just simply return back. If the data hasn't arrived from the DRAM yet, it would simply wait here. Once the data comes back from the memory controller, it would just simply return back the data. So how the timeline would look like? The timeline would look like something like this. So you waited for the L1 to finish. Then L2 and LLC access is happening in parallel while the main memory access is also going on. Okay. So you can actually finish this entire memory request and save these many cycles. Note that processor can still stall very much, but at least it will stall for the less number of time. That's performance. Okay. But now the problem is that all of this looks fine on paper, but it actually works if and only if you can make very accurate predictions that which requests are going to off-chip. Because if you are not going to make an accurate prediction, then you have probably ended up in a region that you are accessing DRAM much more than what is needed, right? So that's the problem. And how much accuracy or how much let's say prediction that we are looking at? Consider this: every 100 requests that the processor generates, on average, what we have seen, 2 to 5 requests actually goes to DRAM. Depending on the workloads, obviously, but only 2 to 5 requests are going to DRAM. So it's literally finding a needle in the haystack, that which of these 100 requests, which 2 of them are actually going to DRAM. You need to identify them. And for those requests, you need to access the DRAM as fast as possible. Okay. So for that part, the second part that I mentioned, that for how to predict, we are going to use a we are going to use a perceptron-based predictor. So maybe I can quickly skip through these ones. Okay, so how we are going to make this prediction? So the prediction happens with what we call a multi-feature hash perceptron model. So I'm not sure how many of you are well versed with perceptron in computer architecture. Have you heard of perceptron usage in computer architecture? Where you have heard? Where have you heard that perceptron has been used? That's good. Sorry? Branch predictor, right? What did you say? I didn't get your point. Yeah, branch prediction, exactly. So perceptron, and especially this sort of perceptron category model, they have been extensively studied for branch prediction, because branch prediction has this tendency to come up with an algorithm. Even though you are not providing the algorithm, you know what is the ground truth looks like. If the history looks like this, you know whether the branch has been taken or not taken. Using that, you can create a kind of data set, and you can train a perceptron model. So this is an analogous situation here, that a history, a feature, whatever you call it, right? And given that feature, you know whether this request has been gone to off chip or not. So you are going to use this information to train a perceptron-based predictor, and so that in future it's also going to correctly identify what's going to happen. Okay, so let's see how it makes the prediction. So what happens is that whenever you have so whenever you have a new request coming up from the core, right? So you extract some sort of features. Like for example, one feature can be, let's say, which program count, or like which instruction has been issuing this request, and some offset in the sense, let's say in the page of in the physical page, or let's say in the virtual page, which cache line that you are touching. And you can literally think of any other information that also carries any information about the request itself, can be used as a feature. Okay, so you use this feature and you hash it down. You use a hash function. That hash function gives you some sort of index that you index to these weight tables. Each weight table gives you some sort of numeric like integer weights, right? So the weight can be, let's say, -4, it can be 12. It means something. So what does it mean? It can actually range from -16 to +15. So it means basically if it is either on the end, right, it's either positively saturated or negatively saturated. It basically says that you either have a positive correlation or the negative correlation. Means if that feature reappears, it's definitely that it's not going to be off chip, or if that feature reappears, it's definitely going to be off chip. That's a strong positive correlation or the strong negative correlation. But if you have if you have weights around 0, so that means that feature doesn't convey any meaningful information at all. Okay, so what we're going to do is, once you get the weights for all the features, you're simply going to sum it up and use this sum, feed it to an activation function. Activation function sounds fancy. It's as simple as testing with some predefined threshold. So in this case, 3 is greater than -2. You are going to predict that, okay, it's going to go off chip. Okay, so now how exactly we are going to train this thing? Because on paper it's like, okay, I mean, it's magic going on. How it's exactly is going to go to the ground truth? So let's say for this prediction itself, it predicted that it would go off chip, but it actually shouldn't go off chip. What happens in this case? If it doesn't go off chip, then what would you do? You know that, okay, your activation shouldn't have happened. So that means the sum of the weight should have been lower than the cumulative weight should have been lower than the activation threshold that we have set up, right? So in this case, what you are going to, so you are getting an information that, okay, your weights might have been higher than expected. So you need to downgrade it, the weights. So what you're going to do, you're going to relook this same weight tables again with the same feature information, get the weights that give you that same weights that you ended up using prediction, and just simply decrement all of their values. So if you simply decrement all of their values, next time when you're going to reappear with the same feature, you probably have, the weights would get saturated lower than the activation, thus maintaining the balance. Is this clear to all of you? I still can see some confused things, but you can try it out. I would say, let's say the code is online, so you can try it out, or maybe we can discuss offline also if that's not clear. But so let me show you some evaluation quickly. So we have actually evaluated this work against like lots of workloads, as well as different type of prefetches also, because you can easily see that this is exactly going hand in hand with the prefetching policy, because prefetching is also supposed to do the same thing, right? It's supposed to hide the memory access latency. You are also hiding the memory access latency, so maybe there is an overlap. So we tried to evaluate with all sorts of prefetchers, all sorts of prior off-chip prediction mechanisms, also with a varying degree, like how they have implemented. And then we also have an ideal off-chip prediction which knows it very ground truth way that this request would go off-chip, and you have made that decision on the go. So that gives us a headroom performance, right? So what we and these are the some configuration parameters that I'm not going to go through detail. But so this is the wow. Okay, animations are completely broken. Okay, so this is the performance that finally looks like. So Hermes is on the the orange bar, and then Pythia is on the blue bar. So what you can see is that Hermes might not be as powerful as a full-blown prefetcher like Pythia, which can not only anticipate this request, but it can probably anticipate much many requests further ahead in the stream, right? So definitely Pythia has much more performance improvement. But the beautiful part is that Pythia consumes almost 25 KB of storage, while Hermes actually consumes less than 4 KB. So Pythia literally provides, Hermes literally provides more than half of the performance of what Pythia can provide with only using 1/5 of its overhead. So you all of a sudden you got a different design points. Probably it's not as powerful enough as Pythia itself, but it's good enough. Okay, but now the good part is that if you enable both of them together, then that additively provides you 5.4% more performance. So that's basically says that even if you have both of these running together in the system, additionally they can provide performance. So that's win-win, right? And the third thing is that if you look into the ideal Hermes, which has the ideal information availability, we are clocking near to the 90% performance of what ideal prediction can provide. So we are also very much close. But don't consider that this is a 90% performance of the ideal benefit doesn't mean that the accuracy is also 90%. So accuracy is lower. I'll go to that. But so that's one thing. The second thing is maybe I'll skip this one. But the key takeaway from this figure was that if you try to take a look into the accuracy part of the problem, let's say how much bandwidth increase that Pythia is causing, Hermes is causing, and Hermes plus Pythia is causing. If you compare this one, so what it shows that Hermes, consider that the Hermes actually has half of the performance benefit, right? But then Hermes only increases the DRAM transactions by 5.5%, whereas Pythia actually increases the DRAM transactions by 38.5%. So you are literally getting half of the benefit by not improving the DRAM transactions even close to that one. So when Hermes is working fine, it's giving you a very targeted set of performance improvement without having lots of bandwidth overhead. Okay, so that's the whole goal. Now, if you try to map this thing with the performance benefit that we have shown in the past, right? So what it actually shows that for every single point performance benefit that these two things provide, if you deploy Pythia to get this, you would improve you would increase bandwidth by 2%. If you use Hermes, then Hermes on top of Pythia, you would break even by 1% performance benefit comes with 1% increase in bandwidth. But then if you simply deploy Hermes as is without having Pythia on the chip, then for the same 1% performance benefit actually comes with only 0.5% bandwidth improvement. So it basically shows that Hermes has better performance to bandwidth overhead ratio. So for every single unit bandwidth overhead, you are getting much more benefit than what full-blown prefetcher can provide. Okay, so I'm not going much more details into these figures. There are lots of evaluation points in the paper, different prefetcher points also, and then these are some overheads that we have mentioned, 4 KB only, and then power overhead is also very negligible. But yeah, if you're interested, definitely check out the work. But I just want to summarize that Hermes actually advocates for the off-chip load prediction, which is a different form of speculation than what the address prediction, what the prefetcher does, right? And then off-chip load prediction can either be applied by itself, as I said, like just vanilla Hermes, or it can be combined with the load address prediction to provide additional performance benefit. Okay, and on paper, so the numbers look something like this. So you have accuracy 77%, you have coverage of 74%, and then you have performance improvement as well as performance for bandwidth improvement also. But that said, accuracy can be improved for sure. So if you have any idea that can improve the accuracy even further, then you can probably provide much more performance benefit than lowering the bandwidth cost also. So if you want to try it out, we have open source all of these infrastructures online. So you can get all of these things pretty much out of the box. You just you need to probably implement some of the train predict functions, and you would get outputs like this out of the box. So with that, I would conclude the talk here, and I would ask maybe Konstantinos, you can also start preparing, and then I can just conclude. So just to summarize that the vision that we have started with, right, that in order to handle the data well, we need to have intelligent architecture that handles the data well as adaptively. So we want to achieve something like this rather than just something human design. Okay. So yeah, so that concludes my talk, and then I'll just hand it over to Constantinos.
If you can get some questions.
I'll get the questions. Yeah. Okay.
Sorry, Hermes looks like it's trying to reduce the latency of this memory request. And at the same time, I don't understand why we should see a benefit when we are combining it with a prefetcher, unless it's trying to fix a look-ahead problem of the prefetcher, right? So it means that the prefetcher is late, so the latency is exposed, and then this method is trying to fix this problem, right? Is the reason why we're seeing this benefit, or it's...
That's one, yes, but that's a good question. So why we're seeing even additive benefits, that, right? So, so these two predictions are kind of different to each other. Like address prediction is predicting the entire address, what might be demanded by processor next. Off-chip prediction doesn't even go that big. It says that, okay, address has been generated by the processor. You're just simply going to predict, given this address, would it go off-chip or not? So we have seen, like, depending on the workloads, there are some workloads you would see that address prediction is a lot tougher. Like there is apparently no pattern going on. The predictor is simply giving you nothing. But even in those workloads, if you just simply say that, okay, in that case, I cannot predict the address. Let's just wait for the code to generate the address. Once the address gets generated, I'm just going to predict whether it's going off-chip or not. In many cases, like surprisingly, that off-chip prediction actually works. So in those cases, what the idea is that even if prefetcher is not working, or probably it's working against you, right? It's probably getting something random, not usable, right? In those cases, probably you can also take prefetcher off and just simply rely on the off-chip predictor. Says that, okay, this is, you aim small, you miss small. That's the idea. So you do whatever you can. If you can have some other prediction also, you do, and then that also.
Okay, but then this follow-up question. Sorry for that.
No.
Go ahead. Yeah, these are good questions. Yeah.
The other strategy would be to always check, right? In this case, where we are always bringing garbage using the prefetcher, technically just always check both the cache and the off memory at the same time. Off chip, sorry.
Okay.
But this is a huge increase in energy, right? Because we're checking.
That's true.
At the same time. So did you perform or evaluate the energy consumption?
We do have an energy evaluation, yes. So the energy evaluation definitely increases by this fact that the cache lookup is not going anywhere. It's going on. But on top of that, if you're wrong, then you're also accessing the DRAM. And DRAM is the prime source of energy. So that's the reason why I said that 77% on paper, it's giving performance, that's fine. But in terms of energy, is actually increasing energy. So if you can make that prediction even accurate, then it would you would probably won't break even on the energy side, maybe, but power side you can actually break even.
Okay, thank you.
Yeah. Okay, so if I can just hand it over to Konstantinos, and if you have any further question, I can take it offline. Thanks, everyone.
So hi, everyone. I guess I'm going to be the last person who's going to deliver a lecture in the EFCL. I'm going to squeeze my propaganda of virtual memory as the last part. So we started 2 days ago with some other work, Utopia, which was about how we can improve address translation by minimizing the page table structures. And in this work, I'm going to show you quickly how we can also leverage the underutilized cache resources so that we can basically increase a lot the translation reach of the processor. And that's our mechanism called Victima. I will not go into the executive summary. I will try to be as fast as possible. Some background first so that we can recap on what we said last week. So we know that the page table stores all the virtual to physical address mappings. And in modern systems use an x86 64 level radix tree. And if we want to access the page table, then we need to perform a page table walk, which means 4 sequential memory accesses. How does address translation flow look like? We need to access the memory management unit, which basically stores the recently accessed PTEs. have a two-level cache hierarchy, a TLB hierarchy. Whenever we miss in that, we trigger the page table walker, which searches in the page walk caches for the intermediate levels. And then if we do not find our data there, our translation there, we search inside the page table which resides in the memory hierarchy. So in this plot, we demonstrate that the average page table walk latency for the modern systems takes at least 137 cycles. So the core spends on average 137 cycles to perform a page table walk, which basically deteriorates performance in these applications. We have high latency page table walks and frequent page table walks, which together lead to high performance overheads. So what is our goal in this work? We want to reduce the page table walk frequency by increasing the address translation reach. But let's give a definition of what address translation reach is. So it's the amount of virtual to physical address mappings which are stored by the processor's TLB hierarchy. So as you can see here, we have a modern processor. And let's say that this modern processor can cover up to a maximum of 3 to 4 gigabytes of translations, which consists of both 4 kilobyte and 2 megabyte pages. So what do we want to do? We want to increase this set. And we basically want to increase the reach and reduce the page table walks. We want our processor to cover more and more and more memory. The most straightforward way, we will increase the size of the TLBs, we will make them really large. In this plot, we demonstrate that in the y-axis, the L2 TLB MPKI, the misses per kilo instructions, in two scenarios. Baseline TLB, 1.5 kilo entries, that's what the Raptor Lake has nowadays, and the 64K entry L2 TLB, a really large L2 TLB. What do we find out? Yes, if we employ a 64K entry L2 TLB, we increase the lot, the reach, and we reduce the MPKI from 39 to 24. How about performance, though? How does that affect performance? So in this plot, we demonstrate the speed up over the baseline system for the 64K entry L2 TLB, but we assume that the latency doesn't change. Even though we made the L2 TLB much, much, much larger, the latency doesn't change. It remains 12 cycles. What do we find out? Yes, if the latency remains the same, really small, we have 5.4% speed up over the baseline system simply by putting more transistors inside the TLBs. However, these benefits do not come for free. And here in this plot, I demonstrate the same exact speed up when the latency is tuned according to our model, the circuit model. And we assume that we have a realistic 39 cycle latency to access the L2 TLB, the 64K entry L2 TLB. And what do we find out? If we have a realistic access latency of 39 cycles, we can only provide the speed up of 0.8% over the baseline system. So this solution is meh. The second solution, large software managed TLBs. And what is this about? So in this plot, we demonstrate, in this figure, we demonstrate the L2 TLB. And whenever we miss in the L2 TLB, we do not have another layer in the hardware, we have a layer in the software. So inside the main memory, we store a data structure, which has the same structure as the hardware TLB. And whenever we miss in the L2 TLB, we go and probe and look up this structure. However, this structure needs to be contiguous in the physical address space. And this is true for every hash table structure that looks like a TLB. What are the drawbacks of this design? High latency. Every time we miss in the L2 TLB, we need to go and access off-chip or in the cache hierarchy for a software-managed TLB entry. Second, contiguous physical allocations. And this, for some of you who might know, it's a big problem in data centers of how you can manage memory to avoid fragmentation. And sometimes it's not even easy to find this sort of contiguous physical space. Third, we need to modify the operating system to handle TLB invalidations, coherence between the L2 TLB and the software-managed TLB, and the replacement of the entries inside the software-managed TLB. Again, we have these two solutions, and unfortunately, both approaches come with major drawbacks. So what's the opportunity we saw? We want to leverage the caches, basically, and we want to store TLB entries in the hardware caches. How do we do that? Every time we are searching for a TLB entry, when we miss the L2 TLB, we will somehow store it in the L2 cache. So when we have a miss next time in the L2 TLB, we will not do a page table walk. We will just retrieve our data from the L2 cache. Where's the benefit? The L2 TLB has, let's say, 1.5K entries with a 12-cycle access latency, and a 2 megabyte L2 cache, as Rahul pointed before, fits around 36x more TLB entries with a low latency, for example, 16 cycles. To remind you here, the page table walk costs 137 cycles on average. If we could trade all our page table walks for L2 cache accesses, for a single L2 cache access, we'd have almost a 10x decrease in the number of cycles we spend on L2 TLB misses. However, will we have interference with actual program data? And because if we place TLB entries inside the caches, then we will have interference between actual data and TLB entries. And the answer is that the L2 cache is heavily underutilized. Right now, we demonstrate here that most of the blocks that we fetch inside the L2 cache experience a reuse of 0. We fetch it, and then we never use it again. And then we basically evict it from the L2 cache. What is our goal in this work? We want to leverage the cache resources, underutilized cache resources, to store TLB entries. What do we achieve through that? We increase the translation rates of the processor. And the key idea is to basically repurpose the L2 cache blocks to store some clusters of TLB entries. This leads to a low latency, having a low latency and high capacity component that backs up the L2 TLB. As an overview, whenever we miss in the L2 TLB, we consult a page table walk cost estimator that tells us, okay, is this page costly to translate or not? If it is, then we take the page table entry block that exists in the L2 cache, which is the actual page table entry, and we transform it into a TLB block. So what do we achieve through that? Upon an L2 TLB miss, we can directly use the virtual address to access this TLB block without walking the 4 levels of the page table. What are the benefits of this scheme? A drastic increase in address translation rates, fully transparent to application OS software, and there is no need for contiguous physical allocations, and it's also compatible with huge pages. Why? Because we can store both translation entries for 4 kilobyte pages, 2 megabyte pages, and technically any page size in the L2 cache. I'm going to walk you quickly through the detailed design. So basically, we need to change 3 major changes. L2 cache modifications. How do we allocate TLB entries inside the L2 cache? And what is the page table cost predictor? With respect to the L2 cache modifications, first, we need to enable accessing the TLB blocks inside the L2 cache with virtual address. Right now, this is not possible. All the entries in the L2 cache are accessed using physical addresses. Second, we need to find out if indeed we have a tag match between our virtual address and the TLB block. I will not go through that, but somehow magically we achieve this. The second, how do we allocate TLB entries in the L2 cache? On 2 occasions, on an L2 TLB miss and L2 TLB eviction. On an L2 TLB miss, what do? We miss in the L2 TLB, we trigger the page table walker as normally, and then we fetch the PTE block. So then we consult the page table cost estimator and we ask the question, is this page costly to translate? Yes. So we will transform it into a TLB block. So on an L2 TLB miss, we simply converted the PTE block to a TLB block. And on an L2 TLB eviction, we asynchronously trigger the page table walk. We consult the page table walk cost estimator. And for the PTE block of the evicted entry, we also transform it into a TLB block. So in this scenario, whatever we evicted from the L2 TLB becomes a TLB block in the L2 cache. How does address translation look like? If we miss in the L2 TLB, we trigger in parallel a page table walk and an L2 cache access. And we do that for performance reasons. And if we find our data in the L2 cache, we abort completely the page table walk because we have a hit in the L2 cache. Second scenario, we miss again in the L2 TLB, we trigger the page table walk, but we have a miss in the L2 cache. We don't find our TLB block there. In this scenario, we need to continue performing the page table walk normally and find our translation with this process. The third part, the page table cost estimator. How do we find out whether a page is costly to translate or not? And we need to insert only those pages in the L2 cache. We do not want to spam and pollute the L2 cache with TLB blocks that are not costly to translate. How do we track that? We extend its page table entry with a frequency and the cost counter, and we update these counters upon every page table walk. So the page table walk cost predictor reads these counters, and it has a comparator tree based on some predefined values to predict whether this page is costly to translate or not. There are more details in the paper. We basically did feature engineering to find out the minimal set of useful features so that we can find out which of these features to consult when figuring out whether a page is costly to translate or not. And finally, we ended up with a two-feature comparator, which predicts these costly to translate pages with 82% accuracy. So in the beginning, we took all these features into account. We basically did feature engineering, and we find a minimal set of features. So we tried with a really big model in the beginning with 10 layers, then with 5, then with 2, and we realized that it's basically a simple problem, and we can model it pretty accurately using a comparator tree. In virtualized environments, address translation looks like this. We have a guest virtual address space. We translate to the host virtual address space, and then we translate to the host physical address space. And Victima can help us in this scenario as well. How? Why, basically? In the L2 TLB, we store right now guest virtual to host physical translations. And in these systems, in modern systems, we don't just have an L2 TLB, we have a nested TLB, which stores guest virtual to host virtual translations. So what do? We basically pollute and access and put inside the L2 cache both nested TLB blocks and normal TLB blocks. Some evaluation results. Again, we extended the Sniper multi-core simulator to implement Victima, and we executed many memory in data-intensive workloads that have address translation bottlenecks. In native execution, we compared against the large software managed TLB, baseline system with transparent huge pages enabled, and two systems with really large hardware-based, hardware-managed L2 TLBs with optimistic access latencies of 12 cycles. And Victima, of course. In the y-axis here, we demonstrate the speed up over the baseline system, and as you can see, Victima achieves a similar performance to the optimistically fast 128K entry L2 TLB. Why? Because we leverage the whole reach that the L2 cache can offer for storing TLB blocks. Where is the speed up coming from? Because we reduce page table walks. So in this plot, we demonstrate the reduction of page table walks compared to the baseline system of all the schemes. And then Victima reduces the page table walks by 50% on average compared to the baseline system. We also did a study where we scale the L2 cache size. What happens when we increase the L2 cache size from 2 megabytes to 8 megabytes? And again, we demonstrate here the reduction of page table walks, and we see that if we employ an 8 megabyte L2 cache with Victima, we reduce page table walks by 63%. And in virtualized environments, we compared against two other state-of-the-art schemes, and we found out that Victima even outperforms the 64K entry software managed TLB, which is the state-of-the-art in virtualized environments, by 12%. We modeled the area and power overheads with MacPath. We compared against an Intel Raptor Lake, and we find out that the area and power overheads are extremely low, down to 0.04 and 0.08%. There's more in the paper. It's uploaded on archive. How do we maintain coherence? There is a new replacement policy to favor TLB blocks in the L2 cache. What is the translation reach we provide, and how the page table cost estimator was implemented. The paper is uploaded on archive. You can find all the information there. It's also open source. We received the Distinguished Artifact Award because we had lots of come and go with the reviewers of the Artifact Committee. And I also released some documentation for whoever wants to find out what's going on, because the code is quite complex. And as a conclusion, I presented Victima. The key idea is to transform the L2 cache blocks that store PTEs into blocks that store TLB entries. We leverage and utilize the resources of the L2 cache. And Victima outperformed by 5.1% the state-of-the-art software managed TLB and achieve similar performance to a 128K entry L2 TLB design without the overheads of area, power, energy, and latency that are associated with such a large TLB design. Thanks a lot, and I'm happy to answer any questions. Yes? Sorry? It's unified. So it depends. This heavily depends on the workloads, right? So there is a trend that is basically followed with respect to the L2 cache. So if your workload, what I have seen at least in my experiments is that when a workload has a really high MPKI in the L2 cache, this usually comes with a really high MPKI in the L2 TLB. So there is no chance, if you have really high utilization in the L2 cache, it's really improbable that you have a high address translation overheads. It's really hard for this to happen, really rare. So there is a pattern going on with respect to data accesses and translation accesses, which if someone does the experiment of like memory intensive workloads and finds out that, for example, we experience tons of misses in the L2 and the LLC, then there should be some translation problem going on as well. But for sure, the address translation problem will not appear if your actual data experience really high locality. That's not a thing. Because if your data experience high locality, then the TLBs will experience high locality as well. Any other question? Okay. Thanks a lot, everyone, for again, thanks for being the last 5 days. I hope you learned stuff.